Okay, so today we're going to talk about chapter 6, and we're looking at a couple of different topics. Really, it's quite a bit in chapter 6. We're going to talk about what is called quantum mechanics. And the electronic structure of atoms, just atoms. Okay, so quantum mechanics and the electronic structure of atoms. Very good. So it's a lot in here. Okay, so the idea here is let's consider the atom. Okay, there's a lot of good videos on the atom out there. I just found one yesterday from the 1950s. It was really good. But essentially, the atom has a little tiny center called the nucleus, right? So we know that. And the nucleus is comprised of, in general, two different types of particles. The first one is called the proton, which is positively charged, okay? And it has a relatively large mass. In fact, most of the mass of an atom is due to its protons and neutrons, the nucleus, right? The nucleus also has a second type of particle, which is called the neutron, which has no charge. So I'm going to put 0 here. It doesn't have any charge, as far as we know, but it also has a large mass. Okay. Outside of the nucleus are these particles, which are called electrons, which are in orbit around the nucleus. Okay, so there could be, you know, for hydrogen, there's only one, but for other atoms, there's a bunch. Okay. And so these are little electrons whipping around the nucleus. And the electron is outside the nucleus. Okay. So these are called electrons. And it has a negative charge. And the mass is small. And we know this from experiment. There's experiments you can do to show the electron is very light relative to the proton. In fact, if you were to normalize it, what you would do is you would say, hey, if we compared the numbers, let's do charge, Q for charge, Q for electrical charge. We would have +1 for the proton, 0 for the neutron, and -1 for the electron, right? The charge of the electron is exactly the same as the proton, but opposite. And then in terms of mass, we would have 1 for the proton, 1 for the neutron, and approximately 0 for the electron. Now, it's not exactly 0. The mass of an electron is equal to 1/1800 the mass of the proton. It's about 1/1800. So it's pretty small. So it's not exactly 0, but the mass number for the electron is 0 because it's so small. The proton is a little bit lighter than the neutron. So the mass of the neutron, is, you know, like 1% greater than the proton. Okay, it's a pretty small difference. They're pretty close to each other, right? So there's your model of this is called the nuclear atom. So we call this the nuclear atom. Nuclear meaning that there's a nucleus at the center. And almost all the mass is right there at the center, right? Because that's where the protons and the neutrons are. They're attracted to each other via some sort of glue called the strong nuclear force. The strong nuclear force holds neutrons to protons. The protons themselves are repelled by each other because they're all positively charged. But if you put neutrons in there, the nuclear force between the protons and the neutrons, that will hold them together, and the atom is relatively stable. Some atoms, which have combinations of protons and neutrons that are not exactly all that stable, they decay away. And it actually puts an upper limit in terms of how heavy an atom can be. Once you get above 90 protons, it doesn't really matter how many neutrons you put in it, they can't hold them together. All those protons are trying to fight each other because they're positively charged. So once you get above 90 or so, it's actually once you get above 82, once you're above 82 protons, these atoms become unstable. And some are more stable, some are less stable, but over time they decay away. So, you know, over time in the Earth's crust, all the elements that are above 82 are slowly, it's a pretty slow process, they're slowly decaying away into lead. Actually, they're decaying away into lead, Pb, which is element number 82. Once you get to 82, they're pretty stable. Okay. All right, so there's your nuclear model. So the question that we're going to look at is, how do you study such a thing? You know, it's tiny, right? So how do you figure out what's going on inside that structure? How do we know that is the structure? There's some very clever experiments people did. But it turns out that the more we look into it, the more we study it, the more careful we are about our studies. It turns out this model is actually a little antiquated. It's outdated. It's wrong in many ways, but it's a useful starting point. So our starting issue here, or our starting point to kind of investigate the structure of the atom, is to consider how we would study it, right? And one way you can study it is through something we have a lot of experience with, and that is visible light, or just light in general. Ultraviolet light, visible light, infrared, all the different forms of electromagnetic radiation. We know that when atoms get really hot, they glow, right? If you put a piece of metal inside of an oven, it gets hot enough, it starts to glow red. If you get it even hotter, it'll start to glow white. And if you get it even hotter, it'll start to glow blue. So things produce light, right? Atoms produce light. And you can even do these cute little experiments where you take salt dissolved in water, dip a little piece of metal into the water, get some of the salt off with it, put it into like a flame on your in your stove, right? The stove top, and it'll start glowing orangish yellow. And if there's other elements, they'll glow at other colors. So definitely light is related to the structure of the atom. So what we're going to do at the beginning is we're going to study what we generally call light. Right, that's the word we typically use for it. But light is actually what we call electromagnetic radiation. Okay, that's what light is. We call it light, but it's actually electromagnetic radiation. And what happens is atoms are able to emit electromagnetic radiation, so they can emit it under certain conditions. And they can also absorb electromagnetic radiation. Absorption. This is called absorption, and this is called emission. Okay, and sometimes they can do the same thing. They can do them both at the same time. Absorb, emit, right? So if something's glowing, it's emitting electromagnetic radiation. Most of the times when we see a color, if it's at room temperature, it's not actually, we're not seeing the emission of light, we're seeing the reflection of light. So electromagnetic radiation can bounce off of things, right? So if something bounces off of a wall and it appears red to you, that's because it's not absorbing the red light that's hitting it. It's absorbing other colors. Your eye sees the light that doesn't get absorbed, right? And so if something appears blue to you, that's usually because it's not absorbing the blue light, it's absorbing the other colors, so it appears blue to you. On the other hand, if something is really hot, like it's in a flame, that's typically emission. It's emitting light because it's so hot. So that tells us that to get this atom to emit light, it generally needs to have some temperature. And there is definitely a temperature relationship that we won't go into in great detail here. Okay. So let's take a look at how we measure electromagnetic radiation. Well, one way we do it is with an eyeball, right? Our eyes are evolved to measure light. So if we have a light bulb, the light bulb is emitting radiation. Different colors, right? It's got all these different colors. And our eyes are sensitive to some of those colors. It's actually done at the molecular level. There's a molecule inside your eye called rhodopsin, and rhodopsin is able to absorb electromagnetic radiation. And when it does, the molecule actually absorbs the radiation and then twists. And when it twists, it actually causes the molecule around it to change its shape, which then stimulates an electrical signal to the brain, to the optic nerve, I guess, right? So, you know, that's essentially a detector, right? Our eyes are detectors. And some animals have detectors that are good for some colors. Other animals have detectors that are good for different colors, depending on the needs of that particular animal. If you think about it, plants are also able to do this, right? That's the idea of photosynthesis, is they absorb radiation. They absorb electromagnetic waves, electromagnetic radiation from the sun or from a lamp, right? You can simulate it with a lamp. So that molecule chlorophyll, or those class of molecules, chlorophyll, are able to absorb electromagnetic radiation and convert that eventually into chemical energy, right? They end up taking carbon dioxide and water, taking the energy from that radiation and using that energy to drive particular chemical reactions, which, you know, eventually lead to the production of starch, you know, starches, and then we eat them, right? So definitely there's energy in this electromagnetic radiation. We'll talk about the energy of them as well, okay? So let's talk a bit about electromagnetic radiation. We could, you know, people run entire graduate level courses on electromagnetic radiation. So we're not going to go at that level. But there are essentially two ways of thinking about EMR, electromagnetic radiation. One is what we call the particle model, which is the idea that if you deconstruct electromagnetic radiation down to its finest detail, there are actually little particles that are responsible for carrying the energy of light. And these little particles are called photons. So every time one of these photons strikes some part of your eyeball, that photon has enough energy to cause that actually what it does is it causes an electron to move from one part of the molecule to another, and then that decreases the strength of a chemical bond, and so then the molecule is free to twist, and that's what causes the perception, the starting point of the perception of light, right? So at the lowest level, at the finest detail, these are called photons, and each photon has, we'll talk about energy, has a certain amount of energy, right? Momentum, right? If something is moving, it has momentum, like a ball. If you throw a ball, it has momentum, it has mass, has velocity. So these photons also have momentum, okay? People have even talked about that you could build a really thin sail made out of something that absorbs light, put it into space, and then the sunlight would cause it to move. It would transfer momentum to the sail, and it would be a way to travel throughout the solar system. And in fact, it's a reasonable theory. You could probably do that. So it's kind of cool, right? That's momentum. So so that's one. It's called the particle model, right? Makes sense. The second way of thinking about light or electromagnetic radiation is what we call the wave model. And here, really what we're saying is that if you look at light, it's really comprised of all these waves. Which are moving, right? These are moving waves. I think traveling is 1L. I'm sorry. Okay. So not particles, but actual waves. Okay. So it turns out, for historical reasons, chemists tend to focus more on the wave model, at least when it comes to the topics we're covering in this chapter, and less on the particle model. And it also turns out that, in fact, both models are partially correct, and that in reality, electromagnetic radiation is really a combination of both. It's really, it is a particle, it is a photon, it is comprised of photons, but these photons also have wave-like properties. So we call them wave-particle duality, right? So in fact, cut to the chase, it's really both. It's what we call wave-particle duality. But what you will find is that if you're in chemistry classes, the wave model is more widely used for various reasons I'm not going to go into right now. Whereas, you know, there's an argument for using particle model in certain contexts, okay? So we're going to focus right now on the wave model. So that means we're going to talk about waves. So there are, one type of wave is called a traveling wave. Okay. So you're familiar with traveling waves. Sound waves are traveling waves, right? Sound moves through the room, it's traveling, right? It's pushing, and it's really, it's compressing and expanding air in a particular pattern so that information, so that energy can be transferred through it. Energy, but that energy has a certain amount of information in it, okay? Water, right? Water is traveling waves, right? When you see a wave on the ocean or a wave on a lake, drop a rock onto the surface of water and you'll see a wave motion, right? That's called traveling waves. Those are called traveling waves. And for right now, we're going to focus on traveling waves. But there are also types of waves which are called standing waves. And standing waves are what you get when you have one wave that's moving in one direction, another wave is moving in the opposite direction, and they combine with each other, they add to each other, and you get this phenomenon where it appears to be a wave that's not moving. It's standing, right? So it's called a standing wave. When we get to electrons, we'll talk about that, okay? But for right now, we're talking about photons, and photons are traveling. We were going to think of them as traveling waves. So when you have, so this is our focus now, when you have traveling waves, there's a relatively simple approach to analyzing them, and that is to consider a graph. Okay, so this is the X direction, and this is the Y direction. So the first, this is a Y. So the first way we're going to do this, I'm just going to draw what's called a simple sine wave, where I'm going to attempt to draw a simple sine wave. It's kind of hard with this stylus. Okay. I'm trying to draw this as a regular repeating pattern, right? That's the idea of a sine wave, is this a regular repeating pattern? Okay. So notice sometimes it's positive, sometimes it's negative on the y-axis, right? So it goes between positive and negative. Okay. It spends, there's as much of it above the x-axis as there is below. There's a symmetry there, right? And it's repeating, right? So for example, it starts here, it goes up very positive, then it comes back down and goes to 0. Then it goes down equally as far negative as it went positive, then comes back to 0. And then it starts it over again, right? This is actually one complete cycle of this pattern. And again, it is a pattern, right? Because now, here, let me change the color. If you look here, See, now it's doing the same thing as it did before. It started at 0, it went up very far positive, then it went back down and very far negative, and then it came back to 0 again. So there's another complete cycle, right? And you could just continue this if you wanted to. I'll do a third cycle, just so you can kind of see this. Okay, this is our X. Here's our third cycle, goes up, positive, comes back down to 0, goes back down to negative, and then comes back to 0. So there's our third cycle, right? And of course, it's kind of arbitrary where we start. So repeating patterns. So where does it start? Well, it starts where it wants to start, I guess. So it's going to go down like this and then come back up, right? So I'm not going to show that complete cycle, but we've got 3 little cycles there, right? 3 complete cycles. And what we're going to do is we're going to say, well, how do we analyze this repeating pattern? Okay. Now, there's many different examples where this happens in nature. You know, one simple physical picture would be, imagine you have like a ceiling in your room, right? So you have this ceiling, and you tied a spring to the ceiling and then put a little weight on the end. And then you pulled that weight down and then just let it go. It would go up and down, and up and down, and up and down, and up and down, and up and down. And that's exactly what this is doing, right? It's going up and down, and up and down, and up and down, and up and down, right? So that's a wave, right? That's a vibration. We sometimes use the word vibration in lieu of, you know, meaning the same thing as a wave. Wave, vibration, cycle. There's other words even that will pop into your head and you'll see them. Okay, oscillation. There's a word, right? Oscillation. Okay, so we want to be able to, you know, to kind of analyze this wave. And so one way we analyze it is by talking about how tall is it? How tall is that wave? Well, the most common way to talk about the height of a wave is to look at the peak, to look at the maximum height of that wave. And the maximum height of the wave is called the amplitude. So I'll put an A here for amplitude. So the maximum height of the wave is called the amplitude. We don't use that very often. The abbreviation is an A. And I'm not even going to talk about the units. You know, we don't need to get into the details of what the units would be. Could be length units, right? It might, you know, if it's something that's doing this, the maximum height might be 0.5 meter, right? So that would be your amplitude. So it could be length units. Okay, so that's the first thing. Notice that you also, you know, the amplitude repeats itself, right? Each one of these has the same height. So it has the same amplitude, right? So the amplitude is the maximum height, and it appears, you know, in a repeating way. Now the amplitude might change. There's all kinds of different types of waves there. Okay. You might also notice that you get, you know, the same height down here. So that's also the amplitude, right? So in a sense, it's really the maximum. So it's really the absolute value of that height, right? Okay. So the second, more important to us, is if I start from right here, just arbitrarily at the origin, and I just look how far I go on the x-axis until the cycle ends, right? So I'm going to draw those 2 points in right there. Okay, it looks like there's a length there. There's a length that we're going on the x-axis until this cycle ends. And we call that the wavelength, okay? So that symbol for the wavelength is a lambda. So lambda, I guess I should be more consistent. The length on the x-axis of one cycle of the wave is called the wavelength. And the symbol for that is a lambda, L-A-M-B-D-A. It's Greek, okay? And that might be a little tricky. Sometimes when you look like, well, where's that going to be? So the easier way to do it is just to note that if you go from one peak to the adjacent peak, the one that's closest to it, that's the same thing. That's also a wavelength, all right? So the wavelength, you can just kind of more easily, in my opinion, it's more easy to tell just by saying how far are these two peaks from each other, right? And that distance there is going to be the same as this distance here, okay? So the distance between two adjacent peaks will tell you what the wavelength is, okay? Now, it turns out that wavelength and amplitude have definite meaning in our experiences, right? So when it comes to electromagnetic waves, the amplitude is essentially related to the intensity of the light. So if something is very bright, it has a large amplitude, okay? If something is very dim, it has a low amplitude. The wavelength is actually related to the color of light that we see. So the wavelength of red light is different from the wavelength of blue light or green light or yellow light. Each color has a specific wavelength, okay? The wavelength is a spatial relationship, right? So what we're saying is when we see light, if it has a particular color, it has a specific wavelength. So blue light is, you know, around a wavelength of 450 nanometers, around there. And red light is around 650 nanometers. Okay, those are the wavelengths of just a couple colors. And it's not exactly 450, so like it could be 440. It's a range of wavelengths, give you the colors. So what I would like to do at this stage, I'm going to show you what's called the electromagnetic spectrum. Okay, so I'm going to come over here. Oops, sorry. Here we go. Oh, I like, let's try this one. This one is kind of cool. Okay. There we go. Electromagnetic spectrum. Okay. What I want to do is I want to talk about wavelength. Okay. The visible light is shown sort of up near the top with all the different, you see all those colors, right? And the wavelengths are in the units of what we call nanometers, 10 to the minus 9 meters. Okay. So what you see, they've broken out visible light into a little band up at the top with the different colors, right? It's right up here. So that's visible light. And so we have all the colors. The way you can remember this is Roy G. Biv. Think of that as the name of someone, Roy G. Biv. So it starts with red, then orange, and then yellow. So there's your Roy. Then G for green, and then B for blue, and then indigo is I, and then violet is V. So blue, indigo, violet, Biv. I don't know anybody named Biv, Mr. Biv, but whatever. So Roy G. Biv, just try to remember it. And the wavelength starts at 700 nanometers approximately for red, and then goes all the way to 400, which is violet. Okay, so violet is the most extreme color we can see on one end, and red is the most extreme on the other end. And notice they are ranges and there's not exact values. So I just gave you a couple. Like I said, 650 was red. Looks like it's about right there. And 550 was blue, but it's actually a range and there's no, actually it's not really defined. This is blue and this is green unless they're very far apart, right? And visible light is produced in different ways, okay? But notice how it's broken out. It's expanded. This is an expansion of a really tiny little sliver of the entire electromagnetic spectrum. It turns out that visible light is a form of electromagnetic radiation that is a part of a huge range of possibilities. The electromagnetic radiation that has the smallest or shortest wavelength are called gamma rays. And gamma rays are all the way over here on our spectrum. This whole thing's called a spectrum, right? So this is called a spectrum for visible light, but this is the spectrum for everything. So not until a couple, really, I think about 170, 180 years ago, we only knew about visible light, because it turns out to study other forms of light, you need technology. Our eyes can't see them. So they were unknown, right? It was just unknown. There are gamma rays, which have the shortest of the wavelengths. There are, notice this is on a log scale. This is 10 to the minus 18, 10 to the minus 16, 10 to the minus 14, 10 to the minus 12. We're going up by orders of magnitude. So it's not like 2, 3, 4, 5. It's like 10, 100, 1,000, 10,000. So these are huge ranges. Notice how the gamma rays are shown as really tight squiggles, right? Because they're short wavelength. The wavelength is short, so that means they don't take up very much space. They're very tightly packed. Turns out there's a relationship with energy with that as well. Then you get to longer wavelengths, which are called X-rays, which are still pretty short by comparison to visible light. Big range of X-rays. Of course, we know we use X-rays for imaging, right? Then we get to the ultraviolet. This is the stuff that causes cancer, right? Ultraviolet wave, but it also gives you a tan. So it's, some people want a tan, some people are afraid of cancer. So it depends on the individual behavior. The wavelength is getting longer. So see how the squiggles are getting more widely spaced? Then they don't even show visible in the range, but it's right after ultraviolet because it's so, visible is actually a very narrow part of this entire spectrum, but it's broken out up at the top in terms of the wavelengths from 400 to, so 400 to 700, remember that. 400 violet, 700 visible. What comes after violet? Ultraviolet, right? So it goes ultraviolet, then violet, okay? Then you get your Roy G. Biv all the way to red. After you get from red, you get to even longer wavelengths, which are called infrared. So red, infrared. Infra means less than. Ultra means more than, right? So ultra, you get violet, then ultraviolet, you get red, and then infrared. Then you get microwaves, which is what we use to cook and communicate with our modern cell phone technology. And then the old cell phones and the old TVs and all that stuff, old radios used radio waves. Radio waves were some of the first to be discovered, okay? So wavelength going all the way out. It's kind of hard for me to read this, but it looks like the furthest out when you get to the radio waves look like they're from 10 to the 0 nanometers out to, is that right? Are those in nanometers? Those are actually in meters, I think, right? Let me see. 10 to the minus, no, I guess those are in nanometers. Yeah, so I guess those are nanometers. So all the way out to 10 to the 8th nanometers would be your radio waves, okay? So notice radio waves take up a pretty broad, but notice how widely spaced they are, right? They're very widely spaced, okay? So they have long wavelengths. So the shortest wavelengths are gamma rays, the longest wavelengths are radio waves, and then visible light is in between. And then the shortest wavelength would be for violet, and the longest wavelength would be for red. and you get the infrared. Okay, the technologies that we use are shown up there above them. Now notice at the bottom, there's another scale called frequency in the units of hertz. And we're going to talk about frequency in a moment, but notice the pattern of the numbers. If you look at the wavelength range, the numbers are getting smaller as you go to the right. So from the left to the right, from radio waves to gamma rays, it's getting smaller, shorter. The terminology we use for wavelength is long or short. So they're getting shorter to the right. But look what's happening to the frequency. The frequency is getting larger as you go to the right. So the gamma rays have the highest frequency. The terminology we use with frequency is not large and small. It's high and low. So the highest frequencies are the gamma rays. The lowest frequencies are the radio waves. Okay? And that's important when we get into energy. So there's a relationship here. As wavelength changes, so does frequency, but in an inverse way. As the wavelength gets shorter, the frequency gets higher. As the wavelength gets longer to the left by radio waves, the frequency gets lower as you get to radio waves. Okay, so let's talk about frequency. We've talked about wavelength. Let's talk about frequency. Now, let's consider that the wave is traveling. Let's assume it's traveling in this direction here. Okay. So what I'm going to do is draw the wave 3 times if I can, at least part of it. Okay. Oops, but that was terrible. Let's try that again. Okay, I'm just going to show part of it. So here's our wave. Okay. So this is, we'll call this time equals 0. So this is at the beginning. Now, I'm going to call this A, B, C, and D. Okay. Now what I'm going to say is that at time equals 1, whatever that unit happens to be, the A is now over here. Okay. Okay, so now here's our A. Our B has moved over to here. And our C has moved over to here. Our D has moved over to there, right? So we've now moved this wave, right? It's moving in this direction. And then we could go even further. Okay. Okay, so now A is over here. B is here. C is here. D is here. And now E is over here. Okay. Oh, I didn't do E, sorry. Just went to D. Okay, so it's moving, right? So this wave is moving from left to right. Okay, it's a traveling wave, right? So the idea then here is that when we're talking about electromagnetic radiation, we're looking at something that's actually moving, okay? And it's probably useful to think of it this way, as to think of the wave as sort of vibrating up and down, okay? It's undergoing sort of like a vibration. Again, think about it in terms of our mass that's hanging on a spring. So here's our mass. Okay, you pull it up, and what does it do? It goes up and down and up and down and up and down and up and down and up and down. It turns out what happens is if you change the mass, okay, if you make it bigger, it goes up and down, but it goes up down slower. It goes slower. On the other hand, if you make it real light, actually, I think it's the other way around. If you make it real light, it goes slower. If you make it really heavy, it goes faster, right? Is that right? I'm not sure. In any case, you can change, by changing the mass, you can change the speed with which this wave, with which this spring goes up and down, okay? So it could go, you know, pretty slow, or it could go real fast. Now, what's happening when we do that? We're changing the wavelength, right? That's changing the wavelength, no question about it. This has a longer wavelength. This one has a shorter wavelength. Okay, so the wavelength changes. However, we're going to define something called the frequency now. And the frequency is this. It's the number of cycles of the vibration per unit time. Typically, the unit time is seconds. So I'm going to write it this way. The number of cycles per second. Okay? So in the old days, we would call that CPS, cycles per second. But today we call it a hertz, H-E-R-T-Z, after Helmholtz Hertz, who did a bunch of research on waves. And the abbreviation for that is HZ, okay? So really, not only by doing this experiment are we changing the wavelength, we're also changing how many cycles of vibration this undergoes every second. And it turns out electromagnetic radiation or electromagnetic waves do the same thing. They cycle through up and down, up and down, and up and down. You can see that they're doing that, right? In time. And so it's really like if I count from here, let's start right here. There's one, I'm sorry, let me count this properly. I'm going to do this more carefully. If we start here, so there's one cycle, there's a second, there's a third, there's a fourth. So that's 4 cycles, right? So there's 1. There's 2. 3. And then 4, right? So there's 4 cycles. If we take the number of cycles, so that's 4 cycles, and we divide that by the amount of time, that will give us the frequency, F for frequency, okay? So it turns out these waves, not only do they have a wavelength, they have a frequency. But if we look at that picture again of the spectrum, here's what you see. As the wavelength moving from left to right gets shorter, the frequency gets higher, right? They're inversely proportional to each other. As one gets larger, the other one gets smaller. But that kind of makes sense, right? Because if something is longer, that means it's going to take more time for it to do its complete cycle. So it's going to be a lower frequency. If something is very short wavelength, it's going through a cycle very quickly. So it's going to be a very high frequency. So in both cases, in both of those scales, the top one, which is wavelength, and the bottom one, which is frequency, the pattern is consistent, right? As the wavelength gets shorter, the frequency gets higher. So we can put that together mathematically very easily. It's a very simple relationship. The relationship between frequency and wavelength. The symbol for frequency is an F, and the symbol for wavelength is lambda, is this. The frequency is proportional to 1 over the wavelength, right? As one gets larger, the other gets smaller. It's an inverse relationship. Remember what we said with gases. How do you turn a relationship, a proportionality, into an equation? You need some constant, right? Well, the constant is C. So it's equal to C divided by lambda. And C is the speed of the wave. It's how fast it's traveling. Now that's very interesting, because if you can measure the frequency and the wavelength, you can measure the speed. Alternatively, if you measure the speed, you just need to measure either the frequency to get the wavelength or the wavelength to get the frequency. Okay? So how fast does a wave travel, right? So how fast does a wave travel? So if you've got this wave and it's traveling in this direction, so now it's over here, how fast does it go? Well, it turns out electromagnetic radiation is a very special type of wave. They travel at a constant value in a vacuum. So if you're in outer space where there's a vacuum, they all travel at the same speed. Doesn't matter what the type of wave is. It could be a gamma ray or a radio wave, the most extreme examples of electromagnetic waves. They all in a vacuum will travel at the same speed, and that speed is called the speed of light. Now I'm going to write down a bunch of sig figs here, 5 of them. There's more, there's like 9. 10 to the 8th meters per second. So there's your speed in a vacuum. In air, they travel pretty close to the same speed, but a little slower. Okay. In general, for the problems that we're going to do in this course, you just need to use this value. You don't have to worry about what they're traveling through. You can just use this value. We could even round it to get an approximate answer. 3 times 10 to the 8th meters per second. Okay. All right, that's called the speed of light. So we know this value. This is given. 2.9979 times 10 to the 8th meters per second. And these two are related inversely. Okay? Frequency is inversely proportional to wavelength, vice versa. We could multiply both sides by the wavelength and have frequency times wavelength is equal to C. That's a perfectly fine way to write it as well. Okay? So the first type of problem that you're going to see on ALEX is how to interconvert. Given the frequency, find the wavelength, or given the wavelength, find the frequency. So let's take a look at an example of that. Okay. Interconverting the wavelength and frequency of electromagnetic radiation. A VHF television station assigned to channel 14 transmits its signals using radio waves with a frequency of 470 megahertz, MHz, hertz, right? Calculate the wavelength of the radio waves. Okay, channel 14. Well, I don't know how old this question is, but I do know the frequencies have changed since they came up with HDTV. There used to be what they called VHF, and then which was channels like 2 through 13. For some reason, they never had channel 1. Channels 2 through 13 was VHF, which is very high frequency. And then they wanted to have more, and their technology got better. So they came out with something called UHV, which was channels 14. Yeah, I thought actually 14 was UHF. So I'm not sure that that is actually correct. I think it was 2 through 13 was VHF. In any case, 14 above was UHF, and it went up to like the 60s or something like that, 50s or 60s, okay? In any case, that's called the carrier frequency. So that's the frequency of the waves that are traveling through the air or traveling through a wire. There's a vibrational frequency. Now think about what that number is, 470 megahertz. Mega is a million, right? 10 to the 6. So that's 470 million hertz. That's how many cycles these waves are vibrating every second. That's a pretty high frequency, right? It turns out visible light is even enormously higher than that. But in any case, the only thing we need to know here is the frequency, which is 470 megahertz. And then from that, we want to calculate the wavelength of this wave, okay? 470 megahertz. So I'm going to write it this way. The frequency of channel 14 is 470 megahertz. So that's why when you hear on the radio 1010, 1010 is kilohertz, 1010 kilohertz. That's the carrier frequency. AM radio is 540 kilohertz to 1,600 kilohertz. If you hear 100.3 or 97.3, that's megahertz. That's FM. FM is in megahertz. So that's 97 million hertz, okay? So TV is higher frequency, so here, because you need more information. So here is our frequency. We want to find the wavelength. Okay, so I'm going to do this. I'm going to write lambda times f is equal to the speed of light. We want to find the wavelength, so we just divide both sides by f. So that would be 2.9979 times 10 to the 8th meters per second, divided by our frequency, which is 470. What's mega? 10 to the 6th. So megahertz. Now hertz is a cycle per second. So typically you can just write it as 1 over second. So 1 hertz is 1 cycle per second. So in terms of units, you just write it as 1 over seconds. Okay. Seconds are both in the denominator, and you're left with meters. Okay. So 2.99779 times 10 to the 8th divided by 470 times 10 to the 6th, and you get 0. Yeah, 0.638 meters. Okay. So radio waves have very long wavelengths. So actually what that's telling you is that if you were to, in space, measure the wavelength of, how long the wave is, how long is this one cycle, it's about 0.6 of a meter. So it's about this long, right? It's pretty big, okay? But that's a very long wavelength. And so comparing that to, say, gamma rays or X-rays or ultraviolet or visible light even, this is a very long wave, okay? Let's see if there's one that's any different. Okay. Let's take a look at this one. So interconverting wavelength frequency. So X-rays have a wavelength small enough to image individual atoms, but are challenging to detect because of their typical frequency. Suppose an X-ray camera uses X-rays with a wavelength of 5.33 nanometers. Calculate the frequency of the X-rays, okay? So notice only one number is given here. That's just the wavelength in nanometers, 5.3 nanometers, 5.33 nanometers. We want to find the frequency. Okay, so the wavelength. And the reason that you can image molecules or structures, the atomic structure of matter using X-rays is because they have such a short wavelength. The wavelength, right, is the issue. If you use a light microscope, you can look at small things, but there's a limit. You can't look at, molecules with light microscopes very easily because there's what they call the diffraction limit, okay? So there's your wavelength. I'm gonna write it in scientific notation, 5.33. Nano is 10 to the minus 9. Nano is small. You've heard of nanotechnology, right? 5.33 times 10 to the negative 9 meters, that's 5.33 nanometers. Now let's find our frequency. Wavelength times frequency equals C. So frequency would be C over wavelength. So that would be 2.9979 times 10 to the 8th meters per second divided by 5.33 times 10 to the negative 9 meters. Meters cancel and you get 1 over seconds, which is a hertz. 1 over seconds, which is hertz. Let's do it over here. Okay. 2.9979 times 10 to the 8th divided by 5.33 times 10 to the minus 9. You get very large, high frequency, 5.62 times 10 to the 16th. 1 over seconds, right? But 1 over seconds is a hertz. So we could use prefixes. People might do that. So 10 to the 15th, let's see, 10 to the 9th is giga. 10 to the 12th is tera. 10 to the 15th is, I think it's exa. So put that over and you have 56.2 times 10 to the 15th, so that'd be 56.2 exahertz. People are starting to do that. They're starting to use those very high frequency prefixes. They're very large prefixes for frequencies, because frequencies were pretty high. Okay. Let's see, what do they want it in? I'm just going to look at what their answer is. 5.62. Oh, peta. I'm sorry, not peta, not exa, peta. P is peta. 10 to the 15 is peta. Right? So if you have 5.62 times 10 to the 16, that is equal to 56.2 times 10 to the 15. And then 10 to the 15 is peta. My mistake. Exa is 10 to the 18th. Okay? So petahertz. Okay. The next issue is now taking a look at energy. So I'll bring this problem up just to take a look at it. So it takes 614 kilojoules per mole to break a carbon-carbon double bond. Calculate the maximum wavelength of light for which a carbon-carbon double bond could be broken by absorbing a single photon. Okay, this is interconverting wavelength, frequency, and photon energy. So now notice the terminology photon here. Photon is the particle model, okay? But as it turns out, electromagnetic radiation is not a particle or a wave, it's actually both. It's wave-particle duality. So let me talk real quickly here about energy of a photon. Okay. If you take one of these photons and it has a wavelength and a frequency, and it's traveling through space, the question is, how much energy does a photon have? Well, we know they all move at the same speed, the speed of light. So how do you figure out? You might consider 1/2 mv squared or mu squared for the kinetic energy, because you know how fast they're moving. But what's the mass of a photon, right? That's the problem. They don't really have mass. So it turns out that the experiments that have been done have shown that the energy of one photon is actually very easy to calculate. It's proportional to the frequency of the photon. All right, so if you know its frequency, you can figure out how much energy it has. Again, there's got to be a constant of proportionality, and the constant of proportionality is h. So h times f, where h is the constant, and it's called Planck's constant. It's called the Planck constant. And the value is 6.626 times 10 to the minus 34. And the units are joules times seconds. It's just a constant of proportionality, okay? So if you want to calculate the energy of a photon, you just need to know its frequency. Likewise, if you know its energy, you can also calculate its frequency, okay? However, we also have this other equation, which says that the wavelength of a photon times its frequency is equal to the speed of light. So what you can do is you can rearrange this equation, right? And substitute that in for frequency here. And now we have a second equation here, which says the energy of a photon is h times c over lambda. And that is also a relationship we have. Okay? So here's the value of h, 6.626 times 10 to the negative 34 joule seconds with units. And now we have a relationship between the energy of a photon and its frequency, but also its wavelength, right? This equation here on the right is just substituting in c over lambda for f from the equation on the left. Okay, now what does that mean? What that means is that if you have a frequency, you have energy. So photons, the higher their frequency, the more rapidly they're vibrating, the more energy they have. Okay, pretty simple relationship. Higher frequency, more energy. But remember, we also have wavelength, right? So the mathematically, the smaller, the shorter the wavelength is, the greater the energy is going to be, right? As this gets smaller in the denominator, the ratio is going to get larger and the energy will get larger. Okay, so let's take a look at that problem again in the context here. There's a units issue that we'll go over, but I want to show this to you. Okay, so they're telling you how much energy it takes to break a carbon-carbon double bond. We'll talk more about that as we move through the course. Calculate the maximum wavelength of light for which a carbon-carbon double bond could be broken by absorbing a single photon. So in other words, if you have a photon with the same amount of energy as that double bond, and it gets absorbed by the double bond, it could break that double bond. Okay, that's essentially the idea. So if you break that double bond, and the amount of energy it takes to break it is 614 kilojoules per mole, what would be the wavelength of that photon that's breaking that bond? And the issue here are the units. The amount of energy they're giving you is not in joules, it's in kilojoules per mole. So I got to show you how we deal with that. So let me write the number down. So the energy that we're trying to break is 614 kilojoules per mole. Right, so essentially what we're saying is you got a carbon-carbon double bond, and you're going to have some photon come in, right? Here's your photon. And it gets absorbed and it breaks the bond into two separate atoms. So the energy is transferred from the photon into that bond, and it breaks it, right? It breaks that bond. So now you've got two separate atoms. So how much energy does the photon have? Well, we know it's this amount. And then from that, can you find the wavelength? But the issue here are these units here. See how it's kilojoules per mole? So what I'm going to do is I'm going to get rid of the kilo, right? So that we can do the arithmetic. Kilo is 1,000, 10 to the 3. So it's 614 times 10 to the 3. That's kilo, joules per mole. Okay, so we got rid of the kilo. But why is the mole in there? The mole is in there because it turns out the amount of energy to break a carbon-carbon double bond is so small. It's 10 to the minus 19 joules that they tend to put the units for a large number of molecules, and a large number of molecules is a mole. So let's remind ourselves that a mole is 6.022 times 10 to the 23rd, right? So what I'm going to do is we don't want to know how much it is to break a mole of these bonds. We want to know how much energy, what the wavelength is to break one of these bonds. So here's what I'm going to do. I'm going to get rid of the mole. I'm going to put a mole of these bonds in the top, and then put the Avogadro's number down at the bottom. What you're doing there is you're asking now, let me put it in perspective. Suppose I said it takes $24 for a dozen eggs. And I asked you, how much does it cost for one egg? Well, you'd say, okay, it's $24 for a dozen. What's a dozen? 12. So I'd say, hey, it's $24 for a dozen. But a dozen is 12. So if I divide it by 12, I'll find that it's $2 per egg, right? That's what you're doing here. We're saying it's 614 kilojoules for a mole, but we don't want per mole. We want per one of these molecules. So you divide by Avogadro's number. Okay? So when you do that, you'll just get, a number for one of them. So 614 times 10 to the 3 divided by 6.022 times 10 to the 23. And now you're going to get a really small number. 1.0196 times 10 to the negative 18 joules, right? The moles are now gone, right? So there's your energy. That's your energy. That's what we want to use. Okay? So the energy to break one of these double bonds is 1.0196 times 10 to the negative 18 joules. And that is equal to HC over lambda. Now, why didn't I put HF? The question was, what's the wavelength in nanometers? Not what's the frequency, but what's the wavelength? So why use this one if they're asking for wavelength? Use this one, right? Use the second one. If they asked for the frequency, you would use that one. Okay? That makes sense? So here's what we have. So we want to find the wavelength. Okay? Okay, so E equals HC over lambda. We want wavelength. So here's the algebra. Multiply both sides by lambda. Right? Lambda over lambda is 1. So that's just equal to HC. But we want to find wavelength. So what do? We divide both sides by E. And there we go. Wavelength is equal to HC over E. So we can just put those numbers in. H is 6.626 times 10 to the negative 34 joules seconds. That's your H. Your C was 2.9979 times 10 to the 8th meters per second. So there's your HC. And then we're going to divide that by E, 1.0196 times 10 to the negative 18 joules. And now your joules are gone, your seconds are gone, and you're left with meters. So your wavelength is going to be in meters. Okay. So let me put all these numbers in. A lot of scientific notation. Every one of these numbers has scientific notation in it. So be careful with your calculator. 6.626 times 10 to the minus 34 times 2.9979 times 10 to the 8th divided by 1.0196 times 10 to the minus 18. And you end up with 1.95 times 10 to the negative 2467. And then the units are meters. Okay, so check through that. Make sure you get the correct exponent, because you have to put all those exponents in correctly. You've got 10 to the negative 34. You've got 10 to the 8th. You've got 10 to the negative 18. All of those exponents got to get rolled into that calculation. You should have 1.95 times 10 to the minus 7. Now the question is, what is the wavelength? But they may want the wavelength not in meters. They might want it in nanometers. So if they want it in nanometers, then you got to do that conversion too, okay? Not sure how Alex wants it, but I want to show you how to do that. 1 nanometer is 10 to the minus 9 meters. So if our wavelength is 1.95 times 10 to the minus 7 meters, 1 nanometer divided by 10 to the minus 9 meters. Okay, so now our meters are going to cancel and we'll have nanometers. What you're going to end up with is 195. Okay, 1.95 times 10 to the 2. And there you go. Now that actually is in the ultraviolet. So visible 400 to 700 nanometers. So that's visible. Going beyond that is infrared. So more than 700 is infrared. Going less than 400 is ultraviolet, UV. Okay, until you get down to like 10 nanometers, I think. Once you get down to 10, then it becomes X-rays. Okay, but in any case, that's close enough that it's ultraviolet. All right, so there you go. So your equations, E equals HF. So if you know the frequency, you can just use that one. E equals HC over lambda. Got that one right there. And then the relationship between frequency and wavelength is equal to the speed of light. So you have those three equations, which are very nice. You also have two constants. C is equal to 2.9979 times 10 to the 8th meters per second. Okay, that gets used in you know, it gets used in this one and that one. And then you got your Planck's constant, which is 6.626 times 10 to the negative 34 joule seconds. We'll talk about the importance of Planck's constant later with another problem in the next section. But that should wrap it up for today. So what we've done is we've taken a look at section 6.1 and 6.2. So starting on Monday, we'll do 6.3 and move forward through the chapter. We got to get all the way through 6.8 by Thursday next week. It's a lot of sections in here. There's a lot of material that we need to get through in the next week. So I wanted to start it a little bit early today. Okay, so good luck. Have a great day. Have a great weekend if I don't hear from you. And good luck on all your tests and all that stuff. And take care.